Hey there, welcome back to the channel. We are back again with the OS3 species. So, yesterday we completed uh, 08 CPU API. It's this one interlude process API, fifth chapter, and we had the homework remaining, so we'll complete that today, and then we'll move to the next, chapter 6, which is about mechanisms, I think. So, first, OS 3 pieces. I guess that's it. We need the GitHub link so we can find the fork.py. I'll open the testing. Yep, cool. Um, we can find the folder here to GitHub. Okay. And the CPU API one, this fork.py. So we do have fork.py. I think I should just clone this repository and I can run stuff inside it, right? And then if I have any tests that I need to do, I can just do it inside this, right? Inside the directory of that specific code. So I'll just show you make this completely rm.f. Yeah, rm.f, it's not that I've done anything interesting. So git clone, step, work, CPU, API. Cool. And if I run fork.py with the flag -s10, well, what does that do? Argument C10, flow percentage 0.7, actions 5, action list, this, pins 3, Okay, try some different random seeds to add more actions dash A to get the hang of it. There is a 50% process creation simulator that shows how processes are created in a single familial tree with the relevant readme. Okay, so let's go for the readme. The readme of that one. Readme 4. 159 pages. Okay. We need to cover this as quick as possible because the the other PDF is also a bit bigger, right? So overview folder.py, the simulator folder.py is a simple tool to show what a process tree looks like when processes are created and destroyed. To run it, just folder.py. What you'll see then is a list of actions, such as whether a process calls fork to create another process, or whether a process calls exit to stop running. Each process that is running can have multiple children or none. Every process except a single initial process, which we call E here for simplicity, has a single parent. Thus, all processes are related in a tree related at the initial process. We'll call this tree the process tree, and understanding what it looks like as processes are created and destroyed is the point of this simple homework. Right, cool. Here is a simple example, -s4. So what happens? So A forks B, B forks C, process tree. Okay. From the output, you can see two things. First, on the right is the initial state of the system. On the right, we have initial state of the system. Do you mean this one or this one? First on the right is the initial state of the system. As you can see, it contains one process A, right? Cool. Operating system often create one or few initial processes to get things going. On Unix, for example, the initial process is called init, which spawns other processes as the system runs. Second on the left, you can see a series of actions, listings in which various actions takes place, and then a question is posed about the state of the process tree is at that point. To solve and to solve and show all outputs, use -c flag as output. Okay, cool. So A forks B, A forks C, B forks D, D exits, A forks E. Okay, as you can see, the expected tree that results shown left to right for a particular operation is shown now. After the first action, A forks B, you see a very simple tree with A shown as B, A shown as B's parent, A shown as B's parent, right? After a few more forks, a call to exit is made by D, which reduces the tree. Finally, E is created as the final tree with A as parent of B, C, and E, which are considered siblings, as the final state. In simplified mode, you can just test yourself by trying to write down a final process tree using dash F flag. By testing to write down the final process tree using the dash F flag, final process tree. Once again, you can use the dash C flag to compute the answer and see if you are close. Oh, okay. Okay, got it. So I can run dash C to guess if my answer was correct. Uh, a number of other options exist in the Fox simulator. You can flip the question around with the dash T flag, which allows you to view the process tree states and then guess what action must have taken place. Okay, you can use different random seeds, dash S, or just don't specify one to get different randomly generated sequences. You can change what percent of actions are forks versus exit with dash F flag. Okay, dash F flag is for percentage of forks and exits. You can specify specific fork and exit sequences with the dash A flag. Okay, or have a A fork B then fork C, C exit, and finally A fork D. Just type we should dash C here. Right, okay. So A forks B, B forks C, C exits, C exits, A forks D, and C exists again. Oh, that's dash C flag. Okay. Okay. You can also show the final output and see if you can guess all the intermediate with the dash of flag. Okay, cool, got it. So that's easy. Uh, Run this and see what actions are taken. Can you predict what the process tree looks like at each step? Use the dash C flag to check your answers. Try some different random seeds or add more actions dash E to get hang of it. Right dash E. Yeah, there is no dash E. Capital E is there, which used to specify the specifics. Okay, so I have a gist of it. So if I run forward by dash S10, yep. So A forks B. So yep, that's easy. A, B, C exits. Okay. A A forks B is what is left. A forks D, so B, D, and then E, then A is forked by B, D, and E. Dash C to it. Yep, that was easy. One control the simulator gives you is the fork percentage, controlled by the dash F flag. The higher it is, the more likely the next action is a fork. The lower it is, the more likely the action is an exit. Run the simulator with a large number of actions, example dash A100, and vary the fork percentage from 0.1 to 0.9. What do you think the resulting final process trees will look like as a percentage changes? Check your answer with dash C. Cool. So dash A100 and dash F. Okay, so let's try. First, let's try with simple dash A100. What is, yeah, S is the seed and dash A100. Yeah, and if I were to do this, see, that's a really big, oh, that's a really big tree, right? Ooh, oh, it goes on for long. Okay, if I were to keep the F100, then it will be, then, okay, so let's try this. Output.txt, right? And if I visit output.txt, it's 3037 lines. I'll delete the output.txt. I'll go for the highest percentage in the good, dash F100. And if I go now, it should be same or larger. Yeah, 5000. It has increased. If I were to make 500 F1, that is smaller band, should be significantly smaller. It's the same thing. Is it because I did not delete it? Let's go. No, it's the same thing. And why is that? Because it's a percentage. It's from 0.1 to, yeah, 1 is basically 100 and 100 is basically 100. Yeah, I understand. So 1 is basically 5600 lines, and if I were to go 0.1, so that should give us 293 lines. Ooh, because most of the stuff is going to be exits. Now, given the output by using the dash "t" flag, example 1 dash fork, given a set of process trees, can you tell which actions were taken? Now switch the output by using the dash "t" flag. Okay, I'm not sure what dash "t" flag does, but let's try. Dash series 100, or I can just not keep it. Dash T was supposed to be what? Put the question around with dash T. Okay, so let's try this. Hmm, that's even easier. Okay, that's easier actually. Okay, one interesting thing to note is what happens when a child exits. What happens to its children in the process tree? To study this, let's create a specific example. Fork P dot y this. Okay, so what is happening over here is A forks B, B forks C, C forks D, C forks E again, and then C exits. So if C exits, then all the children process should have nothing to return. So they will be forced to exit, right? They will be cleaned off. Like your memory is gone. The not this one. Memory is gone, G. Yeah. A forks B, B forks C, C forks D, C forks E, and then C is gone. So we can see, oh, they moved back. They went to the other parent. Cool. Now this is cool. Now that's cool. Okay. However, then C exits. What do you think the process tree looks like after that exit? What do you use? What if you use the dash R flag? Learn more about what happens to orphan processes on your own to add more context. Okay, what is dash R flag? PDE and this C exits. It's C exited. They gave me another line. Huh? I don't know what dash R flag is. What the huh? No. Huh? Followed by parser add option. This is the file that will be compiled and run. It is identical to the above, but adds print statements and such. Parser dot add option dash r local reparent help reparent to local parent. Okay, and why wasn't I able to find this? Wait. How reparent to local parent? Straight. Okay, so it reparents to local parent. But this is just this example, right? What happens to often? What happens to often processes? ChatGPT will be better at this. Just copy this. Okay. And then boom. I'm not even going to think because that's how it should be. If you have trouble learning, just use more AI. If you want to learn about something, don't even work on it. Just use AI. Cool. Okay. What happens to D and E when C exits? What theoretical knowledge? Just tell me what happens in IRL systems. Answer in very short. D and E do not die, and when C do not die when C exists, they become orphan processes and are adopted by a subreaper if configured, or ultimately PID1 system D unit. So C exits, D and E keep running, get reparented to PID1 normally. What is PID1? It is the first user-space process started by the Linux kernel on most modern Linux systems. It's system D. It's important. Its important job here when a process becomes orphan, PID1 or a configure subreaper adopts it. So in your example, C exits, D becomes orphan, system PID adopts DE. Okay, okay. Alternative to system D. No, I just have it up. I just have heard. Oh, it's System 76, not System D. Yeah, right. Something around like people used to fight around something like System 76, System D, and I don't remember that. Just wanted to check. Okay, so let's get back to it. One last flag to explore is the dash F flag, which skips intermediate steps and only asks to fill in the final process tree. Now followed up by dash F to see if you can write down the final tree by looking at the series of actions generated. Okay. Final process type. So A Fox B, B exits, A Fox C, A Fox D, C Fox E. Okay, so it's going to be something like I should draw this. Excalibur. I'm not sure why do I not go to other platforms. The thing is that the font on this, which is so good. Okay, so what they basically mean. So A Fox B, B exits, O A D E C. Oh yeah, okay. So we have. Okay, I need a pencil. Right. So okay. So I have A, which is blocked by C, and then we are told that C Fox, so E is the coffee, something like this, and then something like this. That D is terrible. D, okay, ACED. Yep. Huh? Oh, okay. In that case, I guess B exited, so we don't find B over there. Like, oh. So, okay. So, there's also F. So, I guess if I were to give a single seed, that will be the same every time, right? Okay, cool. So, if I remove this, give 6, 7. So, A Fox B, B Fox C, E Fox D. Oh, that's a lot of Fox. Yeah, okay. Yeah, okay. This is more fun. So, okay. 21 minutes. We need to move fast now. E Fox B, B Fox C, C Fox D. Okay, let's draw this. Right, so I have E Fox B, sorry, B is terrible. E Fox B, B Fox C, C Fox D, and D exits, and C Fox E. D. Yep, I'm correct. Finally, we use both T and F together. This shows the final process tree, but then ask you to fill in the reaction that took place. Okay, this is going to be easy. I'm not going to try that. Okay, just move on, bro. Apache Duso. Huh, this is this is new generation. Old man. So coding homeworks are small exercises where you write code to run on a regular machine to get some experience with some basic operating system APIs. After all, you are probably a computer scientist and therefore you should like to code, right? If you don't, there is only CS theory, but that's pretty hard. Of course, to truly become an expert, you have to spend more than a little time hacking away at the machine indeed. Indeed, find every excuse you can to write some code and see how it works. Spend the time and become the wise master you know you can be. So, homework, code. Okay. In this homework, you are to gain some familiarity with the process management APIs about which you just read. Don't worry, it's even more fun than it sounds. You will in general be much better off if you find as much time as you can to write some code. So why not start now? Write a program that calls fork. If we're calling fork, have the main process access variable, example x. If you click on the stuff, I will remove this, close this, and so why is my OPS on the left mouse? Okay, this is terrible. No, OPS on the right mouse. Then we have this, and then this. Yeah, good. Okay. So, yeah. That a program called that calls fork. Before calling fork, have the main process access a variable x and set its value to something 100. What value is the variable in the child process? What happens to the variable when both child and parent change the value of x? Okay, that is easy. So what I can understand is that x x will be present for both of them, but as a copy. So if I modify x in the child, it should be modified in D, right? That makes sense. Okay, so let's try. So yeah, and then main.c or something. And also add the fork one. So fork, I need to import something. Stored lib and only stored lib, yeah. Stored lib, universal standard library dot h. Stored lib, universal standard library dot h. At least that's what I think it is, like universal standard library, whatever. Yeah, okay. So I have a variable x equal to 100, x equal to 100, and I'll fork it and fork child. No, not child. R's lower. And y. Yep. Super original, right? And if I look at that, if y is equal to 0, so that means it's a child. Printf, this is the child. Printf, uh, this is the child, and what should I print? Well, the value of x. X, value of x, and I'll just modify x. X is equal to 1.1, and then print. I'll just use this copy within this, and then else, and then copy all of this, paste, boom, 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 boom. I'll not do this, do this. This is the parent, and I'll write uh, what was that? Int z is equal to weight. None. Is that it? Do we need to take it in RC weight? Okay. Return code of weight. Yeah. So Z will wait. So parent will wait for the child to complete, and then we'll check what is the value of X. So it should be 100. Cool. So this should prove something. Land main.c, and then read our out. Cool. X is 100 still, because they're completely different processes. And if I were to print the address of X, it will be C, right? That's what I think. Come on. Okay. So print address of X, percentage, what is for pointer? P, U, what is it? Oh, wow, I don't remember it. Dash, yeah, pointer P. Let me just, yeah. Okay. And X, boom, 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 boom. Print F, come on. Let's go. They are the same address. We modify one stuff and the other did not get modified. Why is that? Uh, because it's just like, bro, like, bro. Okay, so they are forks. So they have same virtual addresses since they are the same copy of something, right? That's what I think, at least, right? Cool. I'll check that later. I do have some stuff from yesterday that I did not check, which is how do we create multiple child process simultaneously? I did not check that. And if we are able to create one, what happens? if we are able to create one, I wrote one, instead it should be multiple. If we are able to create multiple, what happens if we wait for, if we wait for only one? And then I had to read about signals, but I did not. Because I did not get time. Also, I'm not going to get time tomorrow also. So I have to manage some stuff, you know. Okay, that's fine. So this is going to be 1 hour, like on 30 minutes. Cool. Write a program that opens a file with open system call and then calls fork to create a new process. Can both the child and parent access the file descriptor returned by open? What happens when they are waiting for the file concurrently, that is at the same time? Hmm. What happens in that case? You can return to the past. Um, if you call open on a file, you get the file descriptor, right? But it's for that process. It's just that, you know, why even think about it, right? So how do we use open? So open before the output. Okay, to wrong you try whatever this is. We open it, this. Hmm. How do we do that? 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 So there is not talk about how we can use open. So open. Okay, the open command of opens a file or directory just as if you had double click the file. Okay, this is the open command, but yeah, it's not going to be often used. Okay, we are just going to R download. You know, that's how this is our main goal. We are going to R download. Boom, bang. Okay. So what I think is open returns a file descriptor or something. No, I don't know. No. Okay. So if you are using at least open, so there should be FCTR. I'm not really sure what that means. Okay, cool. So let's say in this I am trying to open readme.md. So there is a foreign MD, you know, a fork or MD. Yes, I think I should do this. Right. Hmm. Uh, what if I lose RC? Is that how it is supposed to go? Call to undeclared function open, ISO header and data do not support a simulated because of this. Okay, cool. So, what could that be? I can try adding all of this stuff and hope it works. Boom, 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 boom. Okay, it did not. Two few arguments to function call. Okay, so it's worked. It's worked. Open declared here. Okay, open. It needs an integer too. So this should be like how do I get this? Okay, so this is going to create create okay, here we go. So open takes an integer argument, right? Oh update. Okay. So let's try. open. If we are to find some kind of flat similar to what we saw, uh, open. Okay. Oh my God, this is the Macintosh open. Ah, yeah. Interpret const character path and then integer flags, where flags includes access modes such as what are the access modes? Oh, I can just do this. Oh wait, it's open to you, right? Tools for that. No, no, no. Open man, open to open files and directories. This is the general one. Nah, it's the Microsoft one. Okay, so the flags, where are the flags? Okay, the file is open, man, with each write to the file also displays there. If path does not exist, create it as a regular file. Okay, but it does exist. So how do we write it, brother? How do we write it? How do we write stuff to it? Get, get, yeah, get. You won't stop. Get. Okay. Can both the child and parent access the file descriptor returned by the open? Well, for now, I'm just going to pass it on create. I hear you. I hear you. I should not be doing that, but I have no choice. It worked and I did not print it. Blah. RC3, if I were to run this again, boom, 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 boom. So it's pretty much every single time RC. Boom. And then we go int new equal to fork. Boom, 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 boom. And if new is equal to 0, so this is a child, child, small child. I'll try to print RC for it. It should be the same, right? So what my assumption is, even if we open it, what happens when I try to write that file? Okay, let's first check whether it opens for both of them or do we get error on one side, right? So this is this, and this, and this, and this, and that. Yeah, yeah. Okay, so it's same for all of them. If I were to write something to it, what's going to happen? Hmm, 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 hmm. Eh, eh, eh. Hey, 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 hey. What's the count? What? What's the count? Polyester cool, white buffer cool, size count cool, or right incorporation. Uh, Solos. Okay, I'm not going to sing that. I've realized my mistakes. Very sad for them. Whatever happened, it hurt me badly, you know. It buffered count length of the buffer. Okay. File descriptor, buffer count. Okay, it's cool. So buffer is buffer to write data from. Okay, cool. So I am just going to go ahead and boom. So I will have a buffer ready. So char pointer x is equal to hello boom. Right? Cool. And then what I'm going to do is that I'm going to write this to something dot haha. Will you try to create two multiple files? Is that it? No, it won't. Because it just checks if it's present and you know it's cool. But we'll also add else so that we can better monitor stuff. Huh? We'll wait for a child. And he said, I don't even have to write that. I can just do this. And then, huh? Okay, cool. Then we write, our child writes for us. RC, comma, the file buffer, so X, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13, boom. And then we write it. I'll try to close this one, right? Because it's a good thing to close. I don't see a something. Oh, I do see a something empty. Oh my god. And it's empty. Come on, man. Come on. We got an error, man. Man. Come on, man. Oh my god, bro. I said right. I said, I said, feet, feet, feet. I said right. I said hi. I said she. I said, I said, I said feet, 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 feet. Oh my god, I shouldn't be singing stuff. Oh, it's going to get copyrighted. Oh my god. Okay, just going to keep it. Yeah. I was going to check, right? No one even would be able to like transcribe what I said, right? Seashells, seashells, on the seashore. Peter Patter, Peter Patter. Wait, I got an error for RC. RC1. What are we doing? What are we doing? RC1, RC1. What? Wait, why did we get another one open? Open is cool, right? Oh, create. Oh, wrongly. Oh my god. Did we miss something? Did you do something? What did I miss? What? Should I include this? Okay. Yeah. Yo, mama. No, it's the same thing, brother. Boom, boom. Cocky eating. It seems like coagulation, and then vein. Oh my god, it's vein. Oh my god, it's using all of the knowledge. It's contemplating now. Oh my god. Okay. Rejuvenating, jittering, something with J. Oh my god, it's something. Are we going to get J? Are we going to get J? J, 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 J. Oh no. I just I Open is reading minus because you're passing OCreate along as the flags. OCreate is not an access mode, it's a modifier. You must OR with one of the O read only, O wrong only, or O this. O read only happens to equal 0. O create by itself silently means O create or O read only. On macOS, creating a new file without write access is rejected. Oh, okay. 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 Invaluable for debugging. Open write. Yeah. Don't care. O create O wrongly. Yep. I should have just copied whatever that was there. Yeah, okay, O wrongly doesn't make sense. O wrongly. Hey, they don't know me, son. Ah, okay, that was a good exercise. I learned a lot of things. I did began to this start with open, and then it calls for to create a new process and with the shell person. I will find this before another open. Yes, I should write answers to this. Alright. Next is the same. Wait, even this, write a program that works this and both the child. Both can access the file. Both can access the file, and the thing is, both can access the file, right? So, uh, why am I not thinking? Think, Aditya, think. Oh my God, stop thinking. What are you doing? What are you doing? What are you doing? Stop thinking. Okay, both can access the file. Both can access the file. Oh my God, my brain is just like I'm trying to answer, and my brain is like, okay, you're not going to answer. But it's like you're my brain. You should help me. And it's like, no, both can access the file. Okay, start thinking. It's not thinking. Okay, both can access the file. Okay, okay. Just going to calm down. Okay, both can access the file. Yeah, that is it. Okay, that's what I was going to say about. Both can access. Yeah, that's it. Sure. I'm not going to fight my brain. What am I talking about? I am the brain, bro. Both can access the file. Yeah, at the same time. I mean, at the same time means the Right under the program is invoke. The child process should print hello. The parent process should print goodbye. You should try to ensure that the child always prints first. You can do this without calling wait in the parent. I'll just call the improved version of the wait. What was that? Wait PID or something? Eh? Is that what you mean? Not called wait means use wait PID? Oh, you want this? Okay, yeah, yeah, yeah. Cool, cool, cool. Let me show you. Non-wait dot py. Or not dot py. Sorry. Did I just create that? Yeah, okay. Yeah, I see how it is. I see how it is. Yeah, I don't see any problem with this, bro. Wait, PID can take a PID, and then it needs stat location and then int options and whatnot. Huh? these are errors which I don't care about because why should we even care about errors? There isn't going to be any error. Is defined above. The start log parameter is defined above. The options parameter contains the difference with the start log parameter is defined above. Where is it? The wait function suspends execution of its calling process until the start log information is available for a terminated shell process or a signal is received or a return from side of the wait call. The wait for call provides a more general interface. Okay, cool, cool, cool. Repeatable organizations if PRD is one, so the call waits for any child process. If PRD is zero, the okay, without wait, you can just do this without wait. How do we synchronize without wait? I haven't learned about it, but have I? Let's check. Have I mark something? Signal is what is signals? Pass. I don't have time to think about it. Oh my god, it's so. I need water. Hello, hello, hello. Audible, audible, audible. Recording, recording, recording. Cool. Wow. By the way, it's a reminder for you too. You should drink water. You should drink a lot of water. You should drink, what is it, 8 liters of water every single day? I definitely do not complete that criteria because I don't move a lot on certain days, and on certain days I just move so much. No, wait PID would be cheating in spirit. It's functionality the same thing as a wait. It blocks a parent until the child exits. Exercise is nudging you towards a real synchronization primitive that lets you this. Okay, I am just going to do this. Just a minute. I'm not visible. No. Good, 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 good. Gulp, 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 gulp. Write a program that calls. No, okay. Yeah. Pipe, most common for this exercise. Read on an empty pipe block. Blocks until data arrives. Oh my god, right. I just piped the output to an empty thing. Right, that's obvious. That is cool. I think. Oh my god. You know what? I mm, okay. Let's just complete this and then we'll stop because I don't think I should be continuing this. Of course, it will be a violation of the treaty that I made that I will be completing every single chapter for the 5 consecutive days. If I'm not able to, then you're not going to see the video. I get it, but I think I've been consistently doing okay, and most important of all, I'm having fun. You played okay. Good job. Okay, so I'm having fun. So yeah, we're just going to get We are like, okay, I'm not going to say. Okay. But I'll continue this. You know, yeah. Uh, what is it doing? Pipe FD, we create an array of two size with pipe FD, zero, read and write and cool. In PID is equal to fork. Okay, print hello. And we'll write X, one size, unblock the parent. Child writes X to this, and we close pipe FD zero, and we close one. Read pipe FD zero, buffer. Hmm. Box until child writes. Very goodbye. Yeah, they are not talking about this. They are talking about this. Okay, so a read on an empty pipe blocks until data writes. I still don't understand what happened over here. So we have pipe FD, an array of size 2. We have the first block as the read end, the second block as the write end. Cool. And then we print hello, and then we write X to pipe FD1, which is the read end. So if someone has to lock the parent, oh, this is so this will print, and this will so by doing this blocks until child writes. So we are waiting for the write. Okay, someone's going to write this. And we are waiting for this read end. I'm going to read. I'm going to read. I'm going to stop, and then we write X to it, and then we close that, close both of them, and then we. Oh, that's cool. That's cool. This is cool. This is cool. Okay, okay, okay. I see how it is. I see how it is. Yo, mama. You know. So I see how it is. I see how it is. I think we can do something much crazier than this. There's a plan cooking in my head. But okay, I get it. I get it. We're still going to write the code ourselves because that's how we become the man. You know, back in my day, I used to yeah, question. Yes, question three. What was the other one? Huh? Okay, so return this and we create an array pipe FD, right, of two size. And why is it two size every single time? What if I do three? What happens if I do three? Let's try that. Pipe FD of size three. What happens? We'll wait for it to read. We read it into character buffer. It was the read end is zero. Okay. No, no, okay, I'm not going to use that. That would definitely give me a copyright. Good. Um, Wait, we have to mention like what size we are reading? Bro. And close. Right, X to this. And then we close all of this again. Right, that is it. We don't have to do anything extra. Cool. Cool. I wish I could have figured it out, but I was not able to. Sorry. Wait, what? We went in world? Seriously? How? Cut a buffer. We did this. Is it because wait, we write to pipe after and we close the read one. So we close the read one first. So that's for this. Write pipe of D1, X1. Write pipe of D1, X1. Read pipe of D0 and buffer of 1. Yeah, no, cat buffer and buffer is the same thing. It's the same thing. Come on, let's not be judgmental. Yeah, then what is happening? Is it because of three dudes or two? It printed X. Cool. We read X. That's how we win. Wars. Not really sure why this doesn't work. So F552, and then why doesn't this work correctly? Again, I don't have time to wait. Earlier I used to have a lot of time that I can just put a lot of time onto a single thing. But okay, I'm a busy man. Customizer. Maybe it's customizer. Really? G, come on, G. It's going to be something related to G. Sifter. Oh God. That is probably the second worst thing there is. Sifter. Sifter. What is it again? Slowly. Okay, that is the first one. $2. What one you called pipe? Oh, I never called pipe. Oh my God, bro. What the hell, bro? What the fuck? Oh, what was that? I see. Oh, right. Yeah, 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 yeah. That should be afterwards. That should be afterwards. Yeah, 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 yeah. Cool. Hold up. Eh, Hold up. Eh, What if I have pipe FT3? Does it only use two? Yeah. Is the regardless of how big your is cool. Cool. So how do we do that? Use pipe. Is it the same text? 13. A very detailed explanation and in a very elegant writing. You know, I'm Joe Marino. Write a program that calls fork and then calls some form of exec to run the program /bin/ls to see if you can try all of the variants of exec, including on Linux, exec cl, cle, clp, cv, cvp, there are some variants of this call. That means trying a lot of stuff, and I am getting tired. 4, 5, 6, 7, 8. A lot of work to do. Man, I'm tired in 3 versions. I did not think that it will take so much time, 1 hour 40 minutes. Okay, we have to boost things up. So this is pure explanation. I know this is going to take a lot of time, so I'm not going to boom do it. Move to this. Now write a program that uses wait to wait for the child process to finish the parent. What does wait return? Wait. Now write a program that uses wait to wait for the child process to finish the parent. What does wait return? What happens if you use wait in the child? What happens if we use wait in the child? Okay, I should be drinking water. No. Technical curiosity is one side, and then drinking water is another side. I'm still wondering. I think I should start streaming, but the thing is that my internet connection sucks. It sucks bad. So question 5.c. Ah, no. Okay, I'm not going to see. Okay. It's- Yeah, what does the weight return? I did not think of that. I should have kept the previous thing. Oh my God, bro. Hold up. A 1785, whatever. Hold up. Oh my God, it's okay. Wait. Okay. Why is it increasing every single time? Yo, what does weight return, bro? Bro, man, piece of weight. What do you return, brother? Hey, oh my God. Man, page of weight, bro. Oh, yeah, that's right. CPID, read parent, what is it return? Okay, I want something better, which is this manson.org. Let's go. Wait, PID, wait ID. Cool. What does it return, brother? What does it return? Wait, on success returns the process ID of the terminated child. Okay, process ID of the terminated child. Wait, returns the process ID of the terminated child on failure. Huh. On success returns the process ID of the terminated child. My on failure, -1 is returned. Who hang clan. Okay, cool. It returns the process ID of the newly terminated something. Okay, cool. It's cool, man. Cool, bro. So, we get this, and then what if we do wait on that? Yeah, we need to try that. This is child, this is parent 1917. Yeah. Minus money on failure because there is nothing to wait for. Huh. Am I correct though? Am I correct? Mostly right, but one correction. Wait returns the PID of the child that terminated, not the parent. Why? The parent is the one calling wait and blocking. The return value tells, okay, that terminated. Yeah, I mean, yeah, that makes sense. Wait child just finished. Everything else is correct. Everything else meaning running wait gives error because there is nothing else to wait for. What is the technical reason for minus one child? The child has no children of its own, so wait sets error number to each child, no child process, and returns minus one. Cool. There was a bug. I just uh, load air on it. That's how I get rid of bugs, you know. That's how I be. That's how they see me rolling. Okay, I'm not going to say. Yeah, whatever the each child thing was, yeah, I'm not going to understand a few of the child. Write a slight modification of the previous program, this time using wait PID instead of wait. When would wait PID be useful? Well, what I wrote about wait PID was that wait PID helps us in. Okay, you know, it's it's getting a bit late. I need to take sleep because tomorrow is a big day for me. Why? No big reason. It's just every single day is a big day, you know. You should. I mean, not you should. You know, there are days that are bad, there are days that are good. But you should try to look at the day in a positive way. Like, you know, I don't want the past mistakes to ruin my future day, right? But yeah, I'll read about them later on. You know, it's not like a big issue. 4, 6, 7, 8 is remaining. I'll complete them. Come on. But then this video doesn't make sense. What is this video even about, right? Homework lecture 2, bro. Okay, write a program that calls fork and then calls some form of exec. Okay. Let me try. Okay, you know what I'll do? I'll skip fork and no one will notice that. They'll think like I'm going to solve it in the future. At the end part of the videos, not going to solve it. But a slight modification of the previous program, this time using wait PID. Okay. What did wait PID do? Warrior, warrior. It takes a PID variable W status int options with when to use PID. Used to wait for state changes. Wait and wait PID. The wait system calls suspends execution of the calling thread until one of its child terminates. One of its child. One of its child. You getting this? You getting this? The call wait and W status is equivalent to wait PID. The wait PID system call suspends execution of the calling thread until a child specified by PID argument has changed state. By default, wait PID waits only for terminated children, but this behavior is modifiable via the options argument as described. The value of PID can be less than -1, meaning wait for any child process whose process group ID is equal to the output PID. -1 means wait for any child process. Bigger means it's the first yawn. Yo, okay, I think I should go to sleep. Okay, it's fine. You know, tomorrow will be a great day. I think so. Tomorrow is not going to be a great day. Okay. But you know, always look at it hopeful. Tomorrow is a fun day. Right? Yeah, I have a lot of things to do, and yeah. Thanks for watching this video. I'm Tabashani, and I am Energy of Fun. Bye.